let's start looking at actual Haskell programs, and let's start with the sub-language of Haskell expressions, which form a very important part of the Haskell language. So to zoom in from the big picture, if you look at Haskell programs as a whole, they are typically made up from multiple files, and these files are called modules. So every file typically contains one Haskell module. And in the beginning, we're mostly going to work with single files and single modules, but even such programs, technically speaking, consist of multiple modules because you're always using libraries in the background, and these Haskell libraries are other files, other Haskell files that are already installed on your machine. So in principle, your Haskell program is always made up of multiple modules. And then within those modules, you have declarations as the main form. There are different forms of declarations, but the most important form of declaration is that of a binding. Bindings introduce new constants and new functions into your program that you can then reuse in other functions and programs. But even in order to write such bindings, you first have to learn about expressions, because expressions are the sub-language that play the central role in bindings. Bindings give essentially names to expressions. So let's start with expressions before we look at anything else. An expression, like in most other programming languages in Haskell, is a possibly nested term that is built up from just constants and function calls. And then there are a few other constructs that can also appear in expressions that we'll look at later, such as let bindings, for example, or case expressions. But primarily, they're built up from constants and function calls. Okay, and one important property that distinguishes expressions from other syntactic categories in the Haskell language is that expressions can be evaluated. Sometimes this is also called reduction. Expressions can be reduced. And if an expression is fully evaluated, then the result is called a value. Values are themselves expressions, right? But they can also be evaluated, but they will evaluate to themselves. So they cannot be evaluated any further, right? And one nice thing about expressions is that GHCi, that is the interactive component of GHC, allows you to just type expressions directly into the interactive environment and have them evaluated for you and get the resulting value back printed by GHC. So let us try to do this. So let me start GHCi, right? And then I get this prompt here, and here I can type in an expression now. Let's have a look at some example expressions, and actually this slide shows expressions that are all values, which you can see observe from the fact that the result that is printed back is always just the expression that you typed in. So if I type in just a number such as 2, but it could also be 5 or 22 or 532, you get just a number back. So all these numbers are expressions, and they're in particular also values. If I type in a list of characters that is enclosed with double quotes, then that is a string in Haskell. There are actually multiple string types in Haskell, but at first we're mostly going to use the basic strings. And basic strings, as it will turn out, are just lists of characters in Haskell. But basically any sequence of characters we can just enclose in double parentheses. In double quotes, and then that is a value as well, a value of type string. There's the option to denote single characters as well, and then you have to enclose them in single quotes. I mean, you can enclose a single character in double quotes as well, then it is a string. If you enclose a character in single quotes, it's a character. What you cannot do is to enclose multiple characters in single quotes. Right? That is not allowed. So if I do something like hello between single quotes, that will yield an error. And actually with an unhelpful suggestion here, which does make sense if you know what template Haskell is, but it is clearly not what we intended to do here. Here we just probably wanted to denote the string hello, for which we should have been using double quotes. Okay, so single quotes only for single characters. Then there are Boolean values, true and false, and they're written with an uppercase T or an uppercase F. And whether a name in Haskell starts with an uppercase or a lowercase letter is often significant. So this really matters. If you write true with a lowercase t, you'll again get an error because that just tries to refer to an identifier called true, which is not defined. So we'll get that true is not in scope. Here we actually get a helpful suggestion from the compiler that we may have wanted to use true with a capital T. Okay. And then this last thing here is an example of a list value, a list that contains the numbers 1, 2, and 4 in this case, written between square brackets and the elements separated by commas. So that is how you write a list, and this is a list value. You can also have list values of lists containing other things, such as booleans. That works as well. That's another list value. And of course, lists can contain more elements if you want them to, or fewer elements. The empty list is the extreme case, which is just written square bracket open, square bracket close. As we will see, lists are homogeneous. They must contain the same kind of things. So a list of numbers is fine, a list of booleans is fine. A list of numbers mixed with booleans is not fine. We'll look at this later. Okay. Now we've seen the most simple kind of expressions, values. Let's look at function calls next. So this slide contains a whole lot of examples of function calls. The first is an application of the logical function not that negates a boolean, so not is applied to true, and that yields false. And here we see already one of the probably most difficult aspects of the Haskell language for beginners, namely that Haskell has a very unusual syntax for function application. Most other languages use parentheses to denote function application, so you would have to write something like this in order to say not is applied to an argument called true. And in fact, Haskell allows this, but in Haskell this is not good style. The space is what denotes function application, and parentheses are only used for grouping, and we will see very soon situations in which we need to use parentheses. But here we don't need to put parentheses around the atomic expression true, right, just to group true to itself. That does not make sense, that's redundant. So while all these are possible, the idiomatic way to write the application of not applied to true is just a space. Okay? And we can apply not to false as well, and then we get true again. All right? Further than that, if we have a function that expects multiple arguments, such as minimum, we can separate the arguments by spaces. So the minimum of 7 and 2 is written min space 7 space 2. And the minimum function then computes the number of the two numbers that is smaller, which in this case is 2. Right? If we had applied it to 2 and 7, we would still get 2. Minimum is a function that expects 2 arguments. So that is a a pitfall here. As you might now think, we can also just compute the minimum of 3 numbers by like doing something like this. This will yield a type error, which we'll talk about later, actually a complicated one. But if you wanted to have a function that computes the minimum of an arbitrary number of elements, you would have to use a different function that is called minimum rather than min, and takes a list, and to this I can give 2 numbers, or I can give 3 numbers, or as many numbers as I like in that list. Right? But min as a function only takes 2 arguments, and if a function takes 2 arguments, then the arguments are also just separated by space, as we see in this call here. Okay? Now in Haskell there are functions that have alphanumeric names, such as not and min, but there are also functions that have symbolic names, and they're called operators. But as I just said, they're also just functions in the sense that they can be defined in libraries and you can define them yourself. I mean, whether something has a symbolic name or an alphanumeric name is just a syntactic choice. Both are functions. So there is no concept of operators being built in, or there being a limited number or a fixed number of operators. Symbolic operators are defined just like functions. The only difference is syntactic, sorry, in the sense that an alphanumeric function such as min or not is typically written in prefix position. So you write the function and then its arguments afterwards separated by spaces, whereas an operator is typically written infix between its 2 arguments. Okay, so plus is written in the middle of 2 and 3. 2 is the first argument to plus, and 3 is the second argument to plus, and 2 plus 3, as you would expect, evaluates to 5. This colon here is another very important operator. It's called cons. The cons operator. This is how you would write it out as a word. That's not the name of it in Haskell. You cannot write cons to 3, 4, 5. That doesn't work. I mean, it's still the name of it, as far as Haskell is concerned, is the colon, but you pronounce it cons. Cons is short for constructor. The idea is of cons that it takes a single element as its first argument and a list as its second argument, and it constructs a new list, that is where cons comes from, that has the first element as its first element and the rest of the elements as the rest of the list. So basically it prepends an element onto an existing list. It's an asymmetric operator, and it can only be used in this asymmetric shape. You cannot like use a list on the left and a list on the right. That will give a type error. And you cannot use a list on the left and an element on the right. That will also give a type error. Again, we'll look at type errors later, but that's the idea. Take is another example of a function with 2 arguments that is written in prefix form. So the first argument of take here is the number 2. The second argument of take is a list. And what take does is it takes the first n elements of the list. So since we apply take to 2 here, it takes the first 2 elements out of this list here. And the first 2 elements out of this list are 1 and 3. Okay. And then finally, map is another interesting function. It's an example of a so-called higher order function because it takes another function as an argument. So map is also applied to 2 arguments here. The first argument is another function called odd. Odd is a function that simply takes a number and tells us whether it's an odd number, so whether it is not divisible by 2. All right. And if we apply map to odd and then a list, then odd will be applied to every element in the list in succession, and the results will be collected as a list again. So because odd applied to 1 is true, odd applied to 2 is false, odd applied to 3 is true, and odd applied to 4 is false again. If we evaluate this, then the result is true, false in a list. Okay. As I just said, operators and functions are essentially one and the same. There are only syntactic differences between the two, in the sense that the default positioning is different. Alphanumeric identifiers are typically written in prefix form, symbolic identifiers are typically written in infix form, but actually you can flip this around. So in Haskell, whenever you have a symbolic identifier, as I said, it's typically written in prefix form with a left and a right argument, but you can move it into prefix position if you enclose the operator in parentheses. So you can write plus apply to 6 and 9 to get 15, but also we had, for example, 2 cons 3, 4, 5. I can move the cons up to the front by enclosing it in parentheses and apply it like this. You can do this with any operator. If I want to compute the product of 7 and 9, I could write this. This is not idiomatic to do it in this way, but it is sometimes useful because it also allows us, as we shall see, to use these operators in isolation. Sometimes we don't want to actually apply them to the arguments in infix form without these parentheses surrounding them. The parser will always expect the left and the right argument to be there, but perhaps we want to pass the product function to another function as an argument, for example, and then we can do it in this shape. We can also go the other way around. If we have a function such as min and max, which takes 2 arguments, we can actually move it into infix position by enclosing it in back quotes. So we had min and 2 and 5, but I could also write 2 and then min between back quotes and 5. Please note that these are back quotes, not normal quotes. Normal quotes look like this in my font, right? So this does not work if these are normal single quotes. Then we are back in the situation where single quotes enclose a character literal, but these are multiple character literals, so this gives some kind of error message that is similar to that. Right? So you have to use back quotes. Maximum works in the same way, and you can actually do this with any function that expects 2 arguments. You can move it in infix position by enclosing it in backticks. So really, whether something is an alphanumeric identifier or a symbolic identifier only sets the default. Okay. Let's look once more at function application syntax. So I said space is function application. Min7, 2 is a function applied to 2 arguments, but sometimes the argument is going to be more complicated than that. The argument of one function may be a call to another function. So perhaps we want to call minimum with 2 arguments, the first being 7 and the second being the result of 2 plus 6. Okay. So if we want to do that, we actually have to enclose 2 plus 6 in parentheses, such as we do here, in order to make it clear to Haskell that the entirety of the expression 2 plus 6 should be seen as the second argument to min. So parentheses are used for grouping here. If we did not place these parentheses there, Haskell would still accept the expression, but as a ground rule, function application binds stronger, as far as Haskell is concerned, than any other infix operator, such as plus. So if we have an expression such as this, then the parentheses are implicitly around this part. So we would compute the minimum of 7 and 2, which is 2, and then add 6 to it, which is 8. Right? So function application binds stronger than operators. That is a good rule to keep in mind. Now let's have some more examples of expressions. So the first example here is a call to reverse. Reverse is another function that operates on a list and just reverses it. So if we look at reverse applied to the list 1, 2, 3, we get 3, 2, 1. And then if we want to reverse the result of this again, we get the original list back. And here, again, we have to put parentheses around the argument to reverse, because the argument to reverse is itself a function application. And if we did not put the parentheses here, then what it would look like to Haskell is like reverse is being applied to 2 arguments. The first reverse call is applied to 2 arguments, the first argument of which is another a reference to reverse, the second argument is the list, and that does not work. Reverse expects 1 argument, does not expect 2, so this gives another error. We'll look at errors later. Okay. Here's another example. Filter is another higher order function, again applied to odd. Unlike map, filter does not produce a list again, which contains all the results of the function being applied to each of the elements. But filter instead applies the function to every element and then keeps only the elements that pass the test. So in this case, it keeps only the odd numbers of the list. So if we look at what filter odd 1, 2, 3, 4, 5 actually gives us, it gives us 1, 3, 5. Okay, and then if we sum this, sum is a function that operates on a list and sums up all the numbers in that list, we get the sum of 1 and 3 and 5, and that is 9. And again, we have to put parentheses around this call to filter, because the entirety of the call to filter is the argument to sum. Now finally, let's look at this example. This shows that strings are actually lists of characters, because take is a function that operates on a list and that can also operate on a string. So actually all functions that operate on lists can also operate on strings. We could do reverse with a string and we would get a reversed string back. So strings are internally just lists. So if we take one element from the string Haskell, we get the string that just contains H. Right? Drop is a function similar to take that removes the first few elements of a list. So in this case, the first 4 elements of Haskell are removed. And then we get ELL. And then we append. Plus plus is a function to append 2 lists or 2 strings, the 2 strings to each other, and we get hell. Now here we don't actually need any parentheses, because the rule kicks in that operators bind less strongly than function application. So take 1 Haskell is 1 call, and drop 4 Haskell is another call, and this plus plus is in the middle, and no explicit parentheses are needed. Okay. One final thing I want to look at is anonymous functions. So Haskell, being a functional language, makes it easy to talk about functions, and in particular we can talk to functions without giving them a name. So here is a way to do so. We can write this expression, lambda x arrow x plus 3. So this backslash here is pronounced lambda, and so we typically say lambda x2 x plus 3 or lambda x arrow x plus 3, and this expression here, which needs parentheses, is the function that takes an argument that is called x and returns x plus 3. So it adds 3 to its argument. We need the parentheses here because otherwise a lambda term, a lambda expression, is extending as far to the right as possible. So if we would omit the parentheses here, then the 4 would also be part of the lambda expression, and then we would get an error because we are trying to apply 3 to 4 here. But we want to use 4 as the argument to the function that is denoted by this lambda term. So we put parentheses here and then use a space and write 4. And then 4 gets filled in for the x, and we get 4 plus 3, which is 7. We can also do this with multiple arguments, so we can write the function that takes a list and a number, n, and then returns a call to take, with the first argument being n and the second being the reversed list. And then we apply this lambda term here to two arguments, the first being a list, in this case a string, hello, and the second being a number, in this case 3. So we get take 3 of reverse hello, and that is giving us the O and the L and the L. Okay, so lambda terms are, for the time being, more a curiosity, but they become really useful as arguments to other functions. So in particular to functions such as map. If we want to, for example, multiply every element in a list by 3 and then add 1 to it, we can easily write it as a map application with a lambda term in the middle. And here, well, I mean, we can give names to functions as well, as we shall see. But here, this, like often, this is a combination that we need in this particular place, and only there. It is much more easy to combine things in place rather than define a separate function, give it a name, and then use that, right? So that's why lambda expressions, lambda terms are also often called anonymous functions, because we do not need to give them a name. And then, of course, the result here is going to be 4, 7, and 10, because, for example, 1 times 3 plus 1 is 4, 2 times 3 plus 1 is 7, and so on. Okay, let's recap. What we've learned about so far is like an important part of the Haskell language, that is expressions. Expressions can be evaluated to values. They consist essentially of constants and function calls. We have seen that functions and operators are more or less the same thing. They just have syntactic differences, whether they are alphanumeric or symbolic, but these preferences of whether they are used in prefix or infix notation can be flipped around by either enclosing a symbolic operator in parentheses or enclosing an alphanumeric operator in backticks. We have also seen all kind of different types of expressions already. We have talked about numbers, characters, booleans, lists, and strings, and also about lambda terms. But we haven't really made that systematic yet. That's the thing that we're going to look at next. The most tricky part from experience to get used to for newcomers to Haskell is actually this function application syntax, getting rid of the idea that parentheses form an integral part of function application syntax, that in principle even multiple arguments are just separated by space, and that parentheses are used for grouping rather than being a part of the function application syntax.